Greetings, this is Dr. Michael DeRoot. I'm going to do a little example of how to do a calculation using buffers in multiple ways. And let's get started. So one of the most common buffers used in biochemical and biological laboratories is TRIS. The Sigma brand name for that is Trisma. It's also known as THAM, T-H-A-M. It's sometimes used medically, but we're just going to focus on the use as a buffer. You can buy TRIS both in the conjugate base form and the conjugate acid form. Those are shown here on the screen, along with their molecular weights, and those come in the solid form. So the question here says, suppose you have both TRIS and TRIS hydrochloride available, and you also have 1 molar solutions of hydrochloric acid and sodium hydroxide. Describe 3 different ways of making 500 milliliters of a 50 millimolar TRIS buffer at pH 7.5. So that's a pretty common thing that you would need to do in a biochemical laboratory, and also for a biochemistry problem for homework or on a quiz. So from here on, I'll just refer to these as TRIS base or TRIS acid or TRIS hydrochloric acid. TRIS hydrochloride, sorry. So let's get thinking about that. What are the 3 ways you could do this? So scrolling up a little bit, you can use the TRIS base and TRIS acid forms in the appropriate ratio, or you could use the TRIS base form and convert some of that into the acid form by using your 1 molar HCl, or you could use the TRIS HCl form, convert that into some of the conjugate base form using your 1 molar solution of sodium hydroxide. Those are the 3 ways. For all 3 of those ways, you will need to know the total amount of buffer in the system, so let's start with that. This is how much you're making, 500 milliliters of 50 millimolar. Now we could convert that into liters and molar if we want to. 500 milliliters would be 0.5 liters, and 50 millimolar would be 0.05 moles per liter. But you can also take your 0.500 liters and just multiply it and keep that in millimolar, because 50 millimolar is going to be 50 millimoles per liter, and that's going to be 25 millimoles. So you can either call that 0.025 moles or 25 millimoles. I'm just going to use this to keep it in nice round numbers. And that would be the total amount of buffer species that you need, both conjugate base and conjugate acid forms. So I'm going to set that equal to the conjugate acid plus the conjugate base, and then I'm going to use the Henderson-Hasselbalch equation in this form. And that will allow me to solve for the ratio of conjugate base to conjugate acid. So let's do that. So the pH that's desired is 7.5. The pKa at 25 degrees C, where we're assuming we're going to do this, is 8.07. Now if you're not at 25 degrees Celsius, there is a correction factor for the pKa. I'm not going to go into that here. So you just get out your calculator, which I'm now doing. Take 7.5, subtract 8.07. You get a negative 0.57. And then take the inverse log of that, or 10 to the negative 0.57. And you get 0.269 is this ratio. Now we have what in algebra class they would say 2 equations and 2 unknowns. You've got an equation that sums the conjugate acid and conjugate base to get 25, and you've got a ratio that is 0.269. So now you can solve those. So let's go ahead and do that. I'm going to just move this right up here and say that 0.269 times the conjugate acid equals the conjugate base, which I got by multiplying both sides by Ca. Now I'm going to plug this in for the conjugate base. So 25, remembering millimoles. I'll just go ahead and write it. So 25 millimoles is equal to 1.269 conjugate acid, and then take 25 divided by that last number, which I've kept in my calculator, and I get 19.70 millimoles. So how much conjugate base? Well, they have to sum up to 25, so just take 25 and subtract that last amount, and you get 5.30 millimoles of conjugate base. That math is going to be the same for all three methods of making the buffer. You need to, however you make the buffer, you need to end up with this ratio. Now let's just think about that for a second and make sure it makes sense. Our pH is 7.5 and our pKa is 8.07. So the pH is somewhat more on the acid side than the pKa, so we would expect more of the conjugate acid, and in fact we do have more of the conjugate acid. We're also not as far as 1 pH unit away from 8.07, so we don't expect the ratio to be, or we do expect the ratio to be less than a 10-to-1 ratio, and it definitely is less than 10-to-1. It looks like roughly 20-to-5, which is about 4-to-1 ratio. So this is a reasonable setup to make a buffer. So now let's go through the three different ways you can make the buffer solution. Method number one. We're going to use the tris base and the tris HCl. So we need 19.70 millimoles of the tris HCl, and we need 5.3 millimoles of the tris base. Now above, we have the molecular weights of those. So let me page back up, 157.6 and 121.14. So this one is 157.6, and this one is 121.14. That's grams per mole, right? We have millimoles, so this is milligrams per millimole. Right? Grams per moles is the same as milligrams per millimoles. This is going to be milligrams per millimoles. Why does that work? Because the millis cancel out, right? So grams per mole, milligrams per millimole, same thing. So now we do the math here. So I'll get out my calculator and take, I'm going to do the bottom one first because I already have that in my calculator. 5.3 times 121.14, and that's 642.26 milligrams. Well, I can't possibly weigh something to that many decimal places, but that's the math. I could probably weigh out to the nearest tenth of a milligram. And then for the other one, 19.70 times 157.6, that's 3,105 milligrams, which would be 3.1 grams, right? And this would be 0.6 grams. So you can do the math in milligrams or grams, but in order to make this one, I would need 3.105 grams of tris HCl and 0.642 grams of tris base. And if the question wants you to describe how you would make that, you need 500 milliliters, 50 millimolar, pH 7.5. So I would say go ahead and get 450 milliliters of deionized water, dissolve in these amounts of the tris conjugate acid and tris conjugate base, and then mix thoroughly, put into a volumetric flask, dilute it up to the mark, and you're done. Method number one. Method number two. Let's do the tris base and hydrochloric acid. So the way this one is going to work is instead of putting in a certain amount of the conjugate acid form and a certain amount of the conjugate base form, we're just going to put in all of the conjugate base form and then convert as much of it as we need to into the conjugate acid form. So in this case, we need 25 millimoles of tris base, all of the conjugate base. And so we do the math there the same way that we did before. 25 times 121.14, so 3029 milligrams of tris base. And now we need to convert 19.7 millimoles of it into the conjugate acid form. Well, we're going to use a strong acid for that, and the strong acid is our 1.0 moles per liter HCl. So how are we going to do that math? We actually need 19.70 millimoles of it. Well, I can't multiply those together directly. I'm going to have to invert the molarity to make that work. So let's just erase that and start with 19.70 millimoles of HCl, and then use my molarity. So it's 1.0 moles per liter, but that also works if I say 1.0 millimoles per milliliter, so it's just 1. So I need 19.7 divided by 1, which is still 19.7 milliliters of HCl. See how that works? So I add all the conjugate base, I add some strong acid, I assume that the strong acid reacts 100% with the weak base to convert that over into the conjugate acid form, and now I have the same buffer that I had when I added the solids of both conjugate acid and conjugate base. So the third way, we're going to use the conjugate acid form and the 1.0 molar sodium hydroxide. So in this case, you need 25 millimoles of tris HCl, and just paging up a bit, that was 157.6. So doing that math, 25 times 157.6, I get 3,940 milligrams of tris.HCl, or if you like, 3.94 grams. And then we need to convert a certain amount of that over into the conjugate base. What's the certain amount? 5.3 millimoles. So we need 5.3 millimoles of sodium hydroxide. And that was also a 1 molar solution, so 1.0 moles per liter, or millimoles per milliliter, and you need 5.3 milliliters of your 1 molar sodium hydroxide. In both of these cases, 2 and 3, right, you would probably dissolve either your tris base or your tris conjugate acid form in your 450 milliliters of deionized water. You would add the HCl or sodium hydroxide, you would dilute it up to the mark, and you would have the buffer. In all three cases, what you would probably do, which I haven't mentioned, is when you, before you dilute it to the mark, you would probably put a pH meter into it, check the pH, and then adjust the pH with HCl or sodium hydroxide to get the exact pH that you want. Because remember, the Henderson-Hasselbalch equation is an approximation, and also if you're working at a different temperature than exactly 25 degrees, then the pKa is slightly different. So if you want the pH to be perfect, you don't just trust the math, you also measure it with the pH meter. So I would go ahead and in my beaker, once I've added the things, I would adjust the pH with NaOH or HCl, then I would dilute it to the mark, mix it up, and then I would measure the pH again because it might have changed a tiny, tiny bit, and I would need to know that. All right, this is another 17-minute video showing you how to do some buffer calculations. I hope it helps. Cheers.